All right, welcome. Today, we're doing something a little different. Think of this as a high-energy coding workout, a full-on array practice marathon. The whole point? To get those problem-solving muscles firing and to build some serious confidence for your next technical interview. Because let's be real, array problems are the bread and butter of these interviews. I mean, mastering them is pretty much a non-negotiable step if you want to land that software development job. So go ahead, lace up your virtual sneakers. Let's get started. So here's our game plan. We'll kick things off with a warm-up to get the fundamentals locked in, then we'll jump into the core challenge with two absolute interview classics. After that, we'll push through a final sprint with a tricky rotation problem, and then finish it all off with a cool down to recap everything we've learned. All right, time for our warm-up. We are starting with two really essential problems, finding the second largest element and, just checking if an array is sorted. Now, they might seem simple, but trust me, they build a super important foundation for thinking about efficiency. Okay, problem number one, find the second largest element. Now, the first thought that probably pops into your head is, hey, just sort the whole array, right? It's easy, yeah, but it's also a pretty heavy operation for what we actually need. A much, much more efficient way to do it is to just walk through the array a single time, keeping track of two variables, the largest number you've seen so far and the second largest. And here's exactly why that matters. Sorting has a time complexity of n log n. That single pass approach, though, that's just O of n. It's linear. For a gigantic array, that difference in speed is absolutely massive. And since both use constant space, the optimized solution is the clear winner. It shows you're thinking about performance, even on the simpler problems. Okay, let's move on to our next warm-up. How do you check if an array is sorted? Well, the brute force way is kind of a nightmare of nested loops, comparing every single element to every other one. But the elegant solution, it's just one single pass. You just check if any number is smaller than the one that came right before it. If it is, boom, it's not sorted. Simple as that. Now, this right here is a perfect example of that leap in efficiency that interviewers are looking for. We go from O of n squared, which gets painfully slow with large inputs, all the way down to a clean O of n. It's a really simple change in logic that gives you a huge performance gain and shows you know how to avoid unnecessary work. Warm-up complete. You're feeling good. Now for the main event, the core challenge. We are tackling two of the most famous, most common array problems you will ever face in an interview, two-sum and maximum subarray sum. First up, the legendary two-sum problem. It's basically a rite of passage. You're given an array of numbers and a target value. Your job is to find two numbers in that array that add up to that target. It seems straightforward, but the way you solve it, well, it reveals a lot about how you think. So, the brute force way to find the pair involves nested loops, checking every single possible combination. That's an O of n squared operation. The optimized solution, though, it's pure elegance. It uses a hash map for instant lookups. As you iterate through the array, for each number, you just ask, hey, is the number I need to reach the target already in my map? If it is, you found your pair, and you did it in a single pass. And here we see a classic trade-off. We make this massive jump from O of n squared time down to O of n time, a huge speed up, but we do it by using some extra memory. Our space complexity goes from constant to O of n because we're using that hash map. In almost every interview scenario, this is a trade that is absolutely worth making. Okay, next up is maximum subarray sum, which is often solved with something called Kadane's algorithm. The core idea is actually really simple. As you walk along the array, you're constantly asking yourself one question. Should I start a brand new subarray right here? Or is it better to extend the one I'm already building? And you only extend it if the previous sum was positive and actually helps you grow. Otherwise, you drop it and just start fresh with the current number. Let's break that down a bit. You have two variables. Max so far, which holds your overall record, and current max, which tracks the best sum ending right where you are. You just loop through the array. At each step, you decide whether to start a new subarray with the current element or add it to your existing one. Then you check if this new current max has beaten your all-time record, your max so far. It's a brilliant, dynamic approach that works great in both C++ and Python. You're doing great. We are in the final sprint now. One last big challenge to really solidify everything we've practiced, the rotate array problem. Let's finish this thing strong. So the task is to rotate an array to the right by k steps. The obvious brute force solution? Just create a new temporary array, place all the elements in their new rotated spots, and then copy that back. It works, for sure, but it uses extra memory.
The optimized way is a surprisingly slick technique called the reversal algorithm, which gets the rotation done in place with no extra memory at all.
The logic here is just fascinating. It sounds totally counterintuitive, but it works perfectly every time. First, you reverse the block of elements that will eventually stay at the beginning. Second, you reverse the block of elements that's going to move to the front. And third, you reverse the entire array, and poof, like magic, everything is exactly where it's supposed to be.
This is the power of a really clever algorithm. Look, both approaches have the same linear time complexity, O of n. But the reversal algorithm pulls it off with O of 1, or constant space. We're not using any extra memory that scales up with the size of our input. This is basically the holy grail of optimization, fast and memory efficient.
And that's it. You've crossed the finish line. The marathon is complete. Go ahead, take a deep breath. Now it's time for the cool down, where we get to review what we just accomplished. You just worked through 5 essential array problems. We covered the foundational checks, then moved on to interview powerhouses like two-sum and Kadane's algorithm, and we finished with a really tricky in-place rotation. That is a fantastic workout. And you know, if there is one thing to take away from all of this, it's that the journey to the solution is what really matters. It's not just about getting the right answer. It's about showing that you can start with a simple, maybe even clunky brute force idea, and then critically think your way to a more elegant and optimized solution. That progression, that is what lands the job. So, how did you do in our marathon today? Be honest with yourself. How many of these 5 problems did you feel confident you could actually solve on your own? Give yourself a score out of 5 and drop it in the comments. We would honestly love to hear how you did. I really hope you enjoyed this array workout. But hey, don't get too comfortable, because next time we're leaving the safety of contiguous memory behind. We're going to dive into the world of nodes and pointers. Get ready for our next workout on linked lists. See you then.